computer science at the University of Naples, that's in southern Italy. And today I'm going to talk about some software qualities. And this presentation is inspired by my recent book called Seriously Good Software, which I published with Manning. You can see the book cover in this slide. So I'll start with the overall message that I'm trying to convey with this talk and this book, and then we'll get into some technical details later about two specific software qualities. But let me start with the most important part, which is this big picture that you see in this slide, which is trying to say that the programmer's journey is a long and complex process made of different steps, and some people would say it's a never-ending journey, probably, where you have to learn more and more as you go along. So what are the main steps in this journey? You start with basic programming. You usually start by learning one or more programming languages. Then you probably need to get into more details on some of the more tricky parts of the language, and most of the times these things are the collections, the generics, or also known as the templates, and the multi-threading are three of the most tricky parts of any modern language. And most of the time, I'll be thinking about object-oriented languages like Java, and my examples will be in Java, but you can apply most of my observations to any other modern language, especially to object-oriented languages. So this first box on the left, let's call it programming or basic programming. And this is what you learn in any school or boot camp. Then we can talk about an intermediate level. I call it programming well, which is know some of the computer science theory that's been developed to support complex programs. And the three main topics that you need to know or to learn are algorithms, data structures, and software engineering. And then the third phase is what I call programming for a living. So practical things you need to use and know to be productive, to be actually productive as a programmer. So to program for a given task, for an arbitrary task that someone else is giving you, programming to a set of specifications and ensuring certain qualities and ensuring that you do it on time, so ensuring a certain speed, a certain productivity. And so you learn about different tools, you learn about different frameworks, and then of course, just as you probably know, you learn to pick up stuff from Stack Overflow, and eventually you learn to contribute to these and to many other websites and forums where professional programmers exchange their knowledge. And what I'm trying to do with my book and with this quick preview that I'm going to give you today is to help programmers cross the middle part of this journey. So help programmers go from the basics towards a professional programmer role. And the way I'm doing this is a little special, which is I'm not going to, and the book doesn't go into the details it doesn't go into the depth of algorithms and data structures. What it tries to do is to look at all these technical things that I'm mentioning here. Look at these things from the software quality perspective. So instead of talking about algorithms and then separately about data structures, I take a different point of view, So I start from software qualities, which are the ultimate goals of a professional programmer: efficiency, correctness, robustness, and so on and so forth. And by looking at these different qualities one at a time, I try to explain how they connect, how they are related to those technical ingredients that I was showing on the previous slides. So how they are connected to algorithms, how they're connected to thread safety. Well, not thread safety is actually one of those qualities. How they are connected to multi-threaded programming, to generics, to collections, to algorithms, to data structures, and to software engineering. So today, in this quick preview, I'm going to focus on two of these software qualities, which are time efficiency and thread safety. So this is the actual summary from the book. And today I'm going to talk about these 4 chapters that you can see in bold. So I wonder if someone else is trying to connect. Would I get some kind of notification? Let me check if I have pending notifications somehow. I don't think I do. So let's go on. So first of all, we talked a little bit about software qualities, right? And in the following slides, I'm going to present to you a problem to solve, and then we're going to see how to solve it in different ways. And this is what keeps the book together. There's a single toy problem, a very simple problem, just to design a single class. And I take this problem through all the chapters, and I show how to implement it to optimize different software qualities, how to implement the same class for time efficiency, how to implement it to improve space efficiency, and so on and so forth. Okay, so let me tell you about this simple problem. It's just a simple example that I need to, that's handy to show how different software qualities interact and what are the main trade-offs. And the example is about water containers. So we're going to design a class representing a water container with 3 operations. First operation, get amount, so measure the amount of liquid in this container. Second operation is to add or remove water from this container. And third operation is to connect 2 of them. And when you connect 2 of them with an imaginary pipe, they will level up. They will share the same amount of water, let's say. In other words, in Java, you end up with the following API. You have a getAmount method returning an amount of water as a double value. You have an addWater method that takes an amount and puts it in this container, in this water container. And you have a third method which connects the current container, so the container you're calling it on, with another container. And connections are permanent. There's no way to remove a connection. Let's see a use case. Like this, I can create 4 empty containers called A to D. And perhaps I will add some water, 12 liters into the first container, 8 liters into the fourth container, and then I will connect the first 2. And then I can ask how much water is in the first container. And the answer is 6, because I put 12 into A, but then I connected A to B, and therefore A and B will share these 12 liters of water. It will, or gallons if you prefer. They will share it, and they will have 6 each. And I also put 8 gallons into D, and so D is not connected to anyone. It just contains its amount, the amount I put in it. Let's add another step. Let's connect B to C and then ask again, what's the amount of water in container A? I get a 4 because the 12 gallons which I originally put into A are now split among 3 containers are split equally because they're connected with imaginary pipes. And so that's the situation. And finally, if I connect B to D, they're all connected now. Some of them are directly connected and some of them are indirectly connected, but it doesn't matter. As long as they are connected in any way, they will split the water. And so we get 5 in each of them because we started with 12 plus 8, 20, and it's now divided equally among the 4 containers. That's your specification. So suppose someone tells you to implement this class. I'd like to take a few seconds to imagine your own implementation in your own favorite language. It doesn't need to be Java. Just think a little bit about what kind of data structure you would use, and then in a few seconds we'll start looking at different ways and comparing different ways to implement this exact specification according to different software qualities. Once again, feel free to ask questions. There's very few of you, so that's certainly not going to be a problem for anyone if you interrupt and ask a quick question. And of course, you can also wait and ask questions at the end if you prefer. All right. So I'll start with what I call a reference implementation, meaning a middle-of-the-road implementation that's not yet trying to optimize any particular software quality. It's just natural, what I think is a natural implementation of this class. And it works like this. Each water container has 2 fields, which are an amount field, representing the amount of water in this specific container, and a group field, which is a set of containers. And its meaning is the set of containers that are connected either directly or indirectly to this one, including this one, because it's easier to have this one as well into the set. It makes our methods simpler. In this way, you don't have to treat this container as a special case. You just treat all containers in the group in the same way. So these are the fields, and let's take a look at the methods. First of all, what does the constructor do? Very simple. So it doesn't need to initialize the amount field, because in Java, if you have a double field like this, it's automatically initialized to 0, and that's okay with us. We only need to initialize the group field with a new hash set, which of course is empty so far. And then as we immediately put this, so that we put the current container, the container that's being created by this constructor, into the set. So the group starts with a single element, which is this same container. I will skip the 2 easy methods, which are get amount and add water, because you can immediately imagine what they do. The get amount, it just returns the value which is stored into this field, and add water is not so obvious because it needs to split water into all containers in the group, but it's still very easy. Okay, you just see how many containers are in the group, you divide the new amount by this number, and then you add that amount to every container in the group. What's more interesting is the third method, which is the connect to method. And This is a high-level description of what the method does. The method itself is like maybe 15 lines, so I won't show it, but let's just agree on what it's going to do. So what it's going to do is the following. First, compute the amount of water which is due in each container after the merge. So we are connecting two containers, but in fact, we are merging two groups. Because remember that groups represent a set of containers that are in any way connected to each other. So now, since we're adding a connection, the two groups of the two containers, of this and other, they now need to be merged into a single group. And everyone in the new group must have, at the end of this operation, must have the same amount of water. So what we need to do is the following. So first, we compute the amount of water which is due in each container after the merge. How do we do this? Well, we sum the amount of water in both groups, and we divide it by the size of the new group, the size of the merged group, which is just the sum of the two old sizes. And let's call this amount new amount. Then we have to merge the two groups into a single set. Let's call it new group. And then we have to update both fields of all containers from both groups, from both of the old groups. So for every container which is either in the first group or in the second group, its new group is the new group. And for every container in the new group, its new amount is the variable new amount. This is how you merge two groups of containers into a single group. Okay, so that was a basic implementation where we were just trying to make things work, but we were not optimizing for any special software quality. Now let's assume we really want to have the maximum efficiency, maximum time efficiency. Okay, before talking about our water containers, let's recall a few basic things about time efficiency. First of all, there is a famous phrase in computer science which says that premature optimization is the root of all evil. That's obviously an exaggeration, but it's a useful guideline, which means before you start to optimizing for any software quality, in fact, not just time efficiency, think if you really need that optimization, because most of the time, if you optimize for something, you are probably going to lose something on other aspects, on other qualities. For example, if you really push time performance to the maximum, you're probably going to have a more messy code, a less readable code, and therefore a less maintainable code. So it's really important for a successful programmer to be able to balance these different software qualities and to estimate in a given context, for a given application, which quality is more important, and find the right balance between different software qualities. That's another high-level, crucial takeaway from my book and from this talk. So first of all, do we really need more speed? Well, it depends on the context, but let's assume for the moment that we do. We need it. Then, standard tool from computer science to ensure that you're doing things properly is to use asymptotic complexity, which is the standard way to measure the trend, so how your performance will change for an increasing size of the inputs. And we are going to talk about this in a second. Then, after you made sure that from the theoretical point of view, your algorithms are optimal or close to optimal or good enough, then comes the practical process of profiling and optimizing your code. And what does profiling mean? It means guessing, or better estimating or measuring the usage profile, meaning how often do the clients call each method. And here, for simplicity, I'm just focusing on a single class, because that's the idea of the book. Focus on a single module, and then, of course, you can generalize these observations to larger systems, but let's focus on the small. On the small, you would like to know how often the clients are going to call each method. And, of course, you may want to estimate or measure, or really measure, how much time the methods actually take. And once you have this information at hand, you would like to optimize, to improve the methods that are either the most common or the most expensive, or both. So the most common according to your usage profile, or the most expensive according to your runtime profile. All right, now let's go back to water containers and consider the asymptotic complexity of the methods. And so let's go back to our reference implementation. We have this amount field and this group field, which is a set of containers. What's the complexity of the three methods? It's quite simple. Get amount is constant complexity, which we write as big O of 1. It means that its time, the time needed by get amount is constant. It doesn't depend on how many containers are around. It doesn't depend on how many containers are connected to this one. It's always the same, because the get amount method just returns the current value of the amount field. On the other hand, both the connect to method and the add water method are not constant time, because they need to loop over the group, or in the case of connect to, they need to loop over two different groups. So in that case, we say that their complexity is linear, because it's proportional to the number of containers that are connected to this one, or the number of containers that the sum of the two groups that we are connecting. But we don't care about these specific details. Let's just say that they are linear. They're not constant, but they're linear. Now, can we do better than this? And first of all, what does better mean in the case where we have different methods? But it's really quite straightforward. Suppose, so this is our current situation, the complexity of the reference implementation. Suppose you find an alternative where add water becomes constant. Is this better than reference? Yes, of course it's better, because the first two methods keep the same complexity, and the third method is faster, because constant is faster than linear. So in technical terms, you can say that this complexity profile, this set of three complexities, dominates this other complexity profile. On the other hand, you may find another alternative, let's call it alternative 2, where connect to and add water have become constant, but on the other hand, the get amount method became linear. Let's just assume you find such an implementation. So is this better than reference? Well, no, it's not better. It's incomparable, because some things are better and some things are worse. Okay, so given this situation, what is it that we are trying to achieve? What would we like to achieve? We would like to achieve an implementation whose complexity profile is not dominated by any other implementation. And if we want to insert a little bit of technical jargon into this observation, we can say that dominance, so when a complexity profile is definitely better than another one, is what mathematicians call a partial order. So some complexity profiles can be compared like these, and other complexity profiles cannot be compared. And any complexity profile which is not dominated by any other is called Pareto optimal. And that's what we would like to find a Pareto optimal implementation, an implementation whose complexity profile cannot be improved any further. Okay, let's do it by little steps. First of all, this was our old profile. Can we just improve, add water, and make it Constantine? This is quite easy to do. The idea is the following. You just need a separate group object. So you need another class which represents a group of containers. And this can be a nested class in Java. So you insert this group class inside the container class because it's a private implementation detail of the container class. And the containers themselves will have a single field now, which is a reference to a group object. So they used to have two fields, amount and group. Now they have a single field, which is the group, and the amount field has been moved inside the group. So this new class called group has two fields, which are basically the same fields that we used to have in the container class, the amount field and the members field. And whenever you create a new container, you create a new group that starts with this container inside. So far, it's very similar to the previous case. It's just that we have moved these two fields in a separate class. Let's call this implementation speed 1, so we will recognize it later. In this picture, I'm trying to show you the difference between the old version called reference and the new version called speed 1. So in the old version, each container knew locally what was the water amount in it, and then it pointed to a set of connected containers, and the set went back to all containers connected to this one. So this is the situation when A, B, and C are connected, and D is isolated. In the new version, we moved all the relevant information into this separate group object, and the containers themselves, they just point to their group. And you can probably see now by this picture that adding water to a container becomes much more efficient on the right. Why? Because on the left, if I want to add 3 gallons to container A, when it's connected to B and C, I actually have to go into the set and modify 3 different objects. Because if I put 3 gallons into A, the effect is to raise the water in A to 5, in B to 5, and in C to 5, because those 3 gallons need to be split among the group. Whereas in the new version, if I add 3 gallons to A, I just need to add 1 to its group. How do I know that I need to add 1? Well, I check in the group how large is the group. And the group knows how large it is because it contains a hash set of size 3. So I take my 3 gallons, I divide the 3 gallons by the size of this set. The result is 1 gallon, and I add this single gallon to this single field here. And so that's how the add water operation went from linear to Constantine. Okay. But connecting two different containers is still linear because you still have to merge two different hash sets. And that takes linear time. Okay, one more step. Can we do in constant time both connect to and add water, but while making get amount slower? This is exactly what I was calling alternative to earlier. Okay, so this is reference. Can we do this when these two are better and this one is worse than before? And this is a little bit trickier because it's tricky to connect two groups of containers in constant time, but it can be done. And the idea is use something called a circular list and another important computer science idea, which is called laziness. So first of all, circular lists. What are the circular lists? Well, we arrange containers in a linked list in such a way that each container points to the next container in its group, and we make it circular. So there's no first and last container in the group. Each container points to the next one. So this would be the situation where containers A, B, and C are connected in a single group. And if you have an isolated container, it just has a pointer to itself. It's a singular list with a single node. And now, the interesting property of these lists is that you can merge two of them in constant time. How? Suppose I give you the two containers B and D, and I tell you to connect them. You only have to exchange these two pointers, these two references. So if you swap the destinations of the red pointer and the blue pointer, you get that B will point to D, because that's where the blue pointer was pointing to, and D will point to C. And as you can see, as a result, we get a single circular list with 4 nodes. And that's exactly how you merge two circular lists. Given any 2 nodes from 2 circular lists, if you swap their pointers, you get a single circular list. And in this way, you can implement. In this way, you can have connect to in constant time. Now, what about add water? How can you make it constant? You make it constant by using laziness. Unfortunately, I don't think I have a slide about laziness, but the idea is the following. When you add water, you normally, so suppose all containers are connected like this, and you add water to A. So normally, without laziness, you would have to modify the amount fields in all 4 containers. On the other hand, as long as no one calls get amount, we don't really care whether the amounts are actually split, are correctly split in different containers. So we can delay the splitting of the balancing of water. We can delay it until the next call to get amount. And that's called laziness. This delaying an operation until you actually need it is called laziness in computer science. It's called being lazy. So to get add water in constant time, we do it laziness. We do it with laziness. When you want to add water to a container, you just add it locally to that container. You don't care about balancing water in the group. On the other hand, whenever you call get amount, you have to scan the whole group. In this case, you have to scan the circular list and actually balance the water amount or compute the correct amount correctly balanced among the group. And that's why you end up with a very fast add water and a slow get amount. But you may want to do this if your usage profile, for example, tells you that users call very, very often connect to and add water, and very, very rarely get amount. So in such a scenario, you may actually want to push all the hard work in get amount and have a very fast implementation for connect to and add water. And we'll see a quick experiment of this type in a few minutes. All right. Finally, okay, so this is the situation for the circular lists. Get amount is low because it must distribute water. Connect to, it merges two circular lists and it doesn't touch water amounts. And add water just adds water locally. Now, can we do even better than this? As you can see, we are pushing all methods towards constant time, but we haven't managed to put all of them in constant time. So obviously, the ideal situation would be to have all three methods very fast in constant time. Can we do that? Can we get this complexity profile? And the answer is no. But we can come very close to that. We can come very close to that with a, let's call it advanced data structure, which is called union find trees. Obviously, I won't go into the details, but let me just give you a feeling of how this data structure works. It's a classical data structure for every situation where you need to maintain some disjoint sets. In our case, these are the groups of containers. It works in every situation when you start with a given set of elements, let's call it E1, En, and initially each element is isolated, just like water containers. And then you only need to have, you can only do two operations on these elements. First, the union operation. Given two elements, merge their sets. And second, the so-called find operation. Given an element, obtain the representative of its set. And this representative is going to be another element, or this element itself. So each set of elements has one special designated element called the representative. So these are the only two operations that this data structure supports. So suppose you want to check if two elements are in the same set. How do you do that? Well, you call find on them. You get the two representatives, and you check if the two representatives are the same, because each set has a single representative. So if you call find on two different elements and you get the same representative, those elements belong to the same set. If you get two different representatives, they certainly belong to two different sets. And if you think about it a little bit, you see that these two operations are enough to implement our water container scenario. Okay, so just a quick preview of how these union find trees are actually built. Each set is going to be implemented as a parent pointer tree. So it's a tree where each node points to its parent, which is usually the opposite of a standard computer science tree, where nodes point to their children. In this case, it's more useful for nodes to point to their parent. But that's technical stuff. We don't go into details here. You can find everything in the book, obviously. And then the union operation consists in merging two trees, and find operation consists in returning the root of that tree, because each set is going to be a tree. So in other words, our groups of water containers are going to be represented internally as trees. And the representative for each group is the root, is the water container that's sitting at the root of the tree. All right, so now what's the complexity of this data structure? What's the complexity of our three methods when we base them on that data structure? And it turns out that the complexity, or more precisely the worst case complexity, is logarithmic in the number of containers, in the number of connected containers. That's not very good, because I told you that we can get very close to constant time, and logarithmic time doesn't seem to be very close to constant time. But the trick is the following, is that there's different ways of measuring asymptotic complexity, and the worst case complexity is not very fair to this in this particular case. So let me quickly remind you the three main ways to measure complexity. So the most used one is the worst case complexity, which is the complexity in the worst possible use case, for the worst possible input or sequence of operations. Then we may measure complexity in an average case way, but to do that, you have to establish a probability over the inputs. So a probability distribution over the inputs. If you fix or if you measure such a distribution, then you can measure the expected complexity over that distribution of inputs. Okay, I want to mention this, but we're not going to talk anymore about this option in this talk. And finally, a third important way to measure complexity is called amortized complexity. And what that means is the average, not over different inputs, but the average over a long sequence of operations. And that's appropriate here. That's appropriate in all cases when algorithms make computational investments for some future benefit. So there are algorithms like these union find trees that sometimes do something expensive, something slow, in order to be faster in the future. And if you measure these algorithms in a worst case point of view, they come out bad, because the worst case is when you actually take that heavy, slow operation, but that's an investment for the future. And if you only look at the worst case, you're not going to realize that that investment is going to pay off in the future. Amortized complexity is the way to emphasize, to give proper recognition to this kind of algorithms, because you take an average over a long sequence of operations. So, and in this long sequence, you may have a few heavy steps in a long sequence of very fast operations. And then you take the average over the sequence, and you perhaps realize that on average, this data structure is very fast. And that's exactly what happens for union find trees. So for union find trees that we use in our third optimized implementation called speed 3, you take as a sequence of operation, a sequence of m operations, any m operations on n containers. And the union find trees, the theory behind union find trees tells you that the amortized time complexity of the whole sequence is proportional to the number of operations times a special function called inverse Ackermann function, which is a function of n, the number of containers. But the good thing is that this special alpha of n function grows extremely slowly. Just think that this number, alpha of n, is at most 4 for all n up to 10 to the 80. In other words, alpha of n is essentially constant, so the complexity of this sequence of m operations is essentially linear in the number of operations, which means that the average cost of a single operation is essentially constant. But only on average, on the average of a long sequence, because from time to time, you may have slow operations. Okay, we're almost done with time efficiency. Let me just show you the whole picture that's in the book about comparing different versions of the water container class. We've seen reference, we've seen speed 1, speed 2, and speed 3. And in this picture, I'm showing on the horizontal axis the space, meaning how many bytes per container when you have 1,000 containers connected in 100 groups of 10. And as you can see, reference is very space inefficient because each container needs almost 60 bytes. And among the versions that we've seen, speed 2, so the one based on circular lists, is the most space efficient with about 25 bytes per container. And in the book, then I show a number of memory optimized implementations called memory 1 to memory 4, which optimize the space. And on the vertical axis, you see the complexity of the slowest method, so that I can compare them on a single axis. And speed 3 is the fastest because all three operations are close to constant time, at least if we measure time in the amortized way. And finally, as promised, let's have a look at real-world experiments. So running these 4 implementations on the following use case: 20,000 new containers, followed by 40,000 water additions, 20,000 connections, and 20,000 call to get amount, one for each container, basically. And as you can see, the time in milliseconds is very, very different from reference, where we were not trying to optimize for speed, to speed 3. We go to 2.3 seconds to about 6 milliseconds. So speed 3 is absolutely destroying reference and speed 2. And in a second experiment, we try to give an advantage to speed 2, which is the one where only get amount is low. So to give it an advantage, we try this extreme use case where we call a lot of times add water, a lot of times connect to, but we only call once get amount. So only when all containers are connected to each other, at the end, we make a single call to get amount. With this very special, very strange use case, we manage to get speed 2 faster than speed 3. As expected, because speed 2 is based on circular lists where add water and connect to are really constant time, are worst case constant time. And get amount is low, but we only call it once. All right. Let's draw some conclusions. Well, once again, before you start struggling and working hard and spending time on optimizing any software quality, in this case, time performance, really ask yourself whether it's appropriate in your application, whether it's appropriate in your context for your job. Conclusion number 1, do not overlook asymptotic complexity. It's not just some theoretical stuff that's not applicable in practice. I think I've shown you that, at least in this case, is very relevant because the actual performances that we measured in those experiments, they mirrored quite directly the asymptotic complexity, the theoretical complexity of those implementations. Moreover, don't stop at worst case. Don't stop at the worst case analysis, but keep in mind that there's different ways to measure complexity that may be more appropriate for your case, may be more appropriate for your algorithm for your data structure. In particular, we've seen the importance of amortized complexity. And finally, regarding profiling and optimizing, pay attention to your usage profile, because as we've seen with the practical experiments, depending on your usage profile, you may prefer a different implementation. Even though I had to use a very extreme usage profile to make another implementation win the performance challenge. And as you've seen, even in this simple example, a single class with 3 methods, there's some non-trivial optimizations you can do, and some of these optimizations are not local to a single method, but actually shift the computational effort from one method to another. So optimizing is not always local to a single method, but you may have to look at the bigger picture, sometimes just at different methods, and see if you can push complexity around from one method to another. And I think I don't have time to actually go through thread safety, because it's already, I think, 12 in the US or 6 p.m. here. So let me skip. Also because this is quite technical. So let me tell you a little bit the high level, what you can find in the book about thread safety, what are the conclusions we can draw from thread safety in this particular case of water containers. So, of course, the whole book is not entirely about this water container example. I may have given the wrong impression, but a good part of the book is about water containers. I think it's a good teaching tool to have a single example that you carry through different software qualities. I think it helps to illuminate, to emphasize the trade-offs when you see what you should do to optimize for one quality, and you see how it's going to mess up another quality, for example. Anyway, my quick high-level conclusions about thread safety is, first of all, well, okay, let me first remind you what thread safety is. Thread safety means whether your class is ready to be used by different threads concurrently, and these different threads shouldn't have to worry about synchronization, shouldn't have to worry about mutexes, if you know about these synchronization primitives, shouldn't have to worry about whether another thread is currently operating on the same containers or not. It should be your container. In this case, talking of water containers, it should be your objects that take the responsibility of ensuring that they can be used concurrently by different threads. That's the definition of thread safety. So a class is thread safe if it can be used by different threads concurrently, and those threads don't need to worry about synchronization. They can use it however they like, and there's not going to be deadlocks, so the program is not going to get stuck, and there's not going to be race conditions. And to do so, my first advice is to establish your concurrency policy. So establish what is it that your threads can do concurrently, and what other operations must be serialized. And once again, you're not asking your clients to serialize those operations. It's your code, it's your class that internally is going to serialize, is going to make non-parallel those operations that are risky if performed in parallel. So that's your concurrency policy. So for example, take water containers. You want to make your water containers thread safe. First, you want to establish your concurrency policy. It's like an internal specification that you may want to write down for your programmers, and it establishes what operations will be allowed to proceed concurrently. For example, if I have two water containers and they are not connected, I can add water to both of them at the same time. These should be allowed, meaning these two add water operations should be allowed to proceed concurrently, because there's no risk of race condition between them, because they're modifying different separate data. On the other hand, if I have two containers and they are already connected, and two different threads want to add water to these two containers, these two operations cannot be allowed to be performed concurrently. They must be serialized, meaning the two threads can call add water whenever they want on these two containers, even if they're connected, but internally, one of these two operations is going to be executed before the other. That's what I mean by they're going to be serialized. They're going to be serialized in a transparent way to the clients. The clients will not know what, they don't need to care about this. But internally, they're going to be serialized. How do you serialize the operations? With mutexes or monitors or semaphores, this kind of synchronization primitives. Now, the case for water containers is particularly tricky because their interactions, so they're arranged in groups, and groups share data, and finally groups change in time, and that's the really tricky part. Groups share data, but you can also merge groups. There's a special operation, as you know, the connect to operation that merges groups. So it's a very tricky case for thread safety. And that's why, as I show in the book, you end up with a tricky solution, which is called lock-free synchronization. If you want to have thread-safe water containers, while at the same time allowing as much concurrency as possible. These two objectives are very tricky to achieve in this particular case. And in general, a final conclusion about thread safety is that getting this kind of low-level synchronization right is very, very tricky. So you should avoid it whenever it's possible. It's a very nice exercise. It certainly builds up your multi-thread knowledge. But in practice, in professional programming, you should try to stay away from it as much as possible. How do you stay away from it? Let's take the case of Java. You stay away from it by using the higher level data structures, the higher level parallel constructs and features that your language offers. For example, in the case of Java, since Java 8, we've had the parallel streams library. And since Java 7, we've had the fork join framework and other stuff. And since Java 5, we've had the concurrent collections. These are high-level, thread-safe classes that have already been tested, and these are what we should use by default. Whereas in the book, if you want to become if you want to become a multi-threading expert, you should know the lower-level primitives, such as implicit monitors, the synchronized keyword, the explicit locks, and so on and so forth. But in practice, you better stick to higher level functionalities as much as possible. And that's my quick summary of thread safety. So finally, we had a quick look of some of the chapters, some of the topics from the book. There's also In the book, I also treat space efficiency, as I said, two different ways to interpret reliability via monitoring and via testing. I talk about an extremely important software quality that's sometimes overlooked even in professional environments, which is readability of code. You may have heard of the book Clean Code. That's one of the best resources about that. And I talk about generality and reusability. Okay, thank you very much for listening. This book took a lot of effort and help from many people at my university. It came out of the class I usually teach, that I've been teaching for about 15 years, and a lot of help from the staff at Manning. As you can see, there's lots of work and lots of people behind every Manning book. Do you have any questions? Nothing? All clear? All right. Thanks again, Dan. Prego. Ciao.